Hi everyone, welcome to episode 3 of the Red Hat Ceph Storage Performance video series. I'm Daniel Parks, working as a consultant at Red Hat. On this episode, we are going to go through the performance results of our testing with block storage using RBD. First, I will give you a quick recap of the cluster setup and the testing methodology that we followed. We explained the setup in detail on episode 1, but just in case you missed it, I will bring you up to speed. On the server side, we have 5 Ceph nodes with 7 NVMe disks per node and 2 OSDs per NVMe. We configured the pool where we created the RBD images with a replication count of 2 and 4096 placement groups. We then created 105 RBD images with a size of 200 gigs each. So we are writing around 4 terabytes of data during the tests. On the client side, we used FIOS RBD IO engine to generate the load, and we had 7 bare metal client nodes. So we configured 15 RBD volumes on each client. We tested with 3 workloads, 3 patterns, with random read, random write, and also with a mixed workload of 70% read and 30% write. On this slide, we have the peak performance we were able to achieve with 4K block size. In the graph, we have IOPS represented in columns, the higher the better, and the horizontal dotted lines are representing the average latency, the lower the better. On the horizontal axis, we have the IO depth of the clients, and we increase the number of the IO depth. So we have 16, 32, and 64. Using higher IO depths increments the number of simultaneous IOs that the clients are pushing to the servers. So we are actually incrementing the load on the server. Staying on the middle ground with an IO depth of 32, we were able to achieve 2 million IOPS with 1.8 milliseconds of average latency for random reads. Random writes peaked at 415,000 IOPS with a latency of 6.2 milliseconds. With our mixed workloads, so 70 read, 30 write, we reached 611,000 IOPS with 3.2 milliseconds of average latency. With this setup, with 105 clients, we can offer around 20,000 random read IOPS and close to 45,000 random write IOPS per client. So as you can see, we have a very high number of IOPS available with very, very low latencies. This is crucial for transactional workloads like relational databases, for example. On this slide, we are going to take a look at the CPU utilization during the 4K tests. As on the previous slide, the vertical axis has IOPS represented by columns and CPU utilization represented by the dotted horizontal lines. Then we have different IO depth on the horizontal axis. We have to take into account that working with huge amount of small block IO is always a very CPU intensive task, not only for the Ceph nodes, but also for the clients generating the load. As we can see on the graph, CPU saturation on the Ceph nodes was reached with an IO depth of 64. Utilization of the CPU is over 80%, taking into account that these Ceph nodes have hyperthreading enabled. That's quite a high value. Checking the CPU performance stats of the OSD nodes, we could see that the CPU run queue was building up during the length of the test. We wanted to be sure to verify that most of the CPU time was being consumed by the OSD processes. So we looked into the stats provided by Ceph Metrics, and we were able to confirm that the CPU utilization was mostly on user. System and I/O weight utilization was very low, so everything was working like expected, and we could confirm that during the 4K tests, one of the factors limiting the performance was the CPU. Let's take a look at the media utilization during the 4K test. In this graph, we have again IOPS represented with columns and the media utilization represented with the horizontal lines. The yellow line that we have here is the random read pattern, and as you can see, it has a very high utilization, around 88% with an IO depth of 32 and as high as 96% with an IO depth of 64. Looking into the NVMe disk stats, we could see that the average queue grew very slowly during the duration of the test. So for random read patterns, we have another resource that is limiting the performance of our testing. Random write and mixed workloads have lower media utilization. The explanation for this is that the BlueStore min alloc size parameter for SSDs is set by default to 16Ks. So all the writes under 16 kilobytes are deferred. Writes that are deferred follow a different data path. The write first goes into the wall device and then asynchronously get written into the OSDs. That's why we see lower media utilization for our random writes. That's because the Intel Optane that we have configured as our wall device is absorbing all the writes during the test. We verified that the Optane disk wasn't getting saturated, and although it had a high utilization, around 90%, we could see that the average queue and the response times were stable during the duration of the test. In this slide, we did a 4K random write client sweep test where we gradually increased the number of clients generating load on the Ceph cluster. In this graph, we again have IOPS in columns and latencies on horizontal lines. The horizontal axis has the number of clients that we use during each test that we gradually increase. One of the things that we can see here is that when we go over 100 clients, there is almost no increase in IOPS because the OSDs are already CPU bound. Also, we can see that when we go over 100 clients, the tail latency starts to increase very, very quickly because we are already saturating the CPU. One positive to take from this test is that under very high load with 140 clients, the cluster is able to sustain very low average latency. That this is always good news. On this slide, we have medium block size results. On the graph, we are comparing IOPS and average latency with different block sizes, 8K, 16K, and 32. As expected, small block sizes showed highest IOPS and lower average and tail latencies compared to medium block sizes. Speaking about throughput, with a random write pattern using 32 kilobytes, the Ceph cluster was able to deliver 6 gigabytes of throughput with only 80 milliseconds of average latency, which is quite impressive. In this next slide, we are taking a look at the CPU and media utilization for medium block sizes. The media utilization is the graph on the left. We can see very high media utilization for random read and mixed workloads, so performance was limited by CPU and media contention. And on the right, we have the graph of the CPU utilization, and we can see that as expected, the CPU utilization decreases as the size of the blocks that we are testing gets bigger. So with bigger block sizes, we have lower CPU usage. In this slide, we're showing large block results. We have 1 megabyte and 4 megabyte maximum throughputs. These are quite big block sizes, especially for block storage with random patterns. But even with random patterns, we wanted to see what was the maximum throughput that we could achieve with this configuration. The blue columns are 4 megabyte block sizes, and we can see that the 3 tests are peaking at around 10 gigabytes per second. This is because the total network bandwidth from the client side to the Ceph cluster was around 10 gigabytes per second. So looking at the resource utilization of the CPU and of the media, we can assume that if we had more bandwidth available on the clients, we could achieve better throughput results. Here with a quick summary of episode 3. With the small block workloads, we can deliver a huge number of IOPS with very low latencies, and our tests were limited by CPU and media contention. Similar to small block workloads with medium block sizes, we found that the limit was the CPU and also the media. And with large block workloads with 4 meg, we were limited by the client network bandwidth. So we were only able to achieve around 10 gigabytes of throughput. So thank you. This is all that we had for episode 3. Thanks for listening. I hope you enjoyed it. And on episode 4, we're going to speak about the performance when we are scaling out our Ceph cluster. So please stay tuned for the next episode. Bye.